Seed pods left after harvesting more valuable parts, such as grain, is considered crop residue and often treated as the non-economic part of crop production. Using a grain residue conversion factor, calculated that the global production of crop residue was 5 billion metric tons in 2021, which is more than 3 times higher than the 1961 production levels. The estimates on the role of crop residue burning on greenhouse gas emission have the highest uncertainty among all the emission categories of the Intergovernmental Panel on Climate Change because of the unavailability of data and uncertain emission conversion factors. The lack of academic focus on the economics of sustainable crop residue management is quite surprising, given that it could play a key role in the farming system by generating subsidiary income, for example, using as livestock feed, increasing crop productivity and profitability, for example, using as soil mulch, and to a limited extent, being used for industrial purposes, for example, biochar and bioethanol production. Furthermore, in connection with climate change mitigation, crop residue retention has a public good dimension to gradually building soil organic carbon pool. Despite its multiple values, government incentives and public campaigns for sustainable use, a large share of crop residue is burned annually with serious consequences for food production, the environment, and the human health. The most conventional and widespread use of crop residue is feed for ruminant livestock. With the increase in global demand for animal-derived foods, which may continue in the near future, one may expect an increase in demand for crop residue as feed. True farmers in many countries value crop residue the same or more than grain. However, there exists a wide variation in the nutrition quality of residues of different crops concerning intake and organic matter digestibility, and a marked preference heterogeneity owing to the differences in the perceived quality among farmers with respect to the use of a given crop residue as feed. These factors, alongside farm mechanization and adoption of modern varieties in agriculture and the local density of ruminant livestock, determine the market value of crop residue as feed. The relative scarcity and hence the perceived value of crop residue could vary significantly even within a region across season. Another use of crop residue is mulch or soil cover, the effects of which are widely documented in the literature, especially in connection with conservation agriculture. The application of crop residue as mulch halts soil erosion by acting as a protective layer to the soil surface, improves physical, chemical, and biological soil properties, stabilizes crop yields, and enhances input use efficiency. In addition, with the recent realization that soil carbon sequestration could form a viable climate mitigation approach, there has been an unprecedented interest in the sustainable use of crop residues in regenerative agriculture. Here, crop residue retention is considered a low cost option to mitigate GHG emission from agriculture. The other use of crop residue, such as thatching for houses, bedding for livestock, substrate for mushroom production, input for paper manufacture, fuel for cooking, and in brick and tile kilns and biochar production gain importance in different contexts and cannot be ignored while developing policies toward more efficient and sustainable use of crop residue. As mentioned above, many farmers overlook the potential use of crop residue, and a large amount is burned annually with varying intensities across countries. For instance, in Brazil, sugarcane pre-harvest burning is widespread, raising serious environmental and health concern. Residue burning is not widely practiced in sub-Saharan Africa, except for cotton and sugarcane. Relatively low cropping intensity and high demand for the ruminant livestock sector curtail the occurrence of residue burning on the continent. On the continent. Although the number of studies that address the issue of unsustainable use of crop residue in Africa is relatively scant. The few existing one point toward problematic residue burning in some countries, Ghana, for example, Ghana. However, it is an Asian country that the residue burning practice poses the highest threat to the environment and human health. The unsustainable management of crop residue is particularly problematic in India and China. For instance, estimated that approximately 24% of 488 million metric tons of total crop residue was burned in India in 2017, resulting in an emission of 824 giga of particulate matter and 211 Tg of carbon dioxide equivalent GHGs to the atmosphere. Rice, wheat, and sugarcane are the major crops contributing to residue burning in the country. The highest incidence of residue burning takes place in the northeastern Indo-Gangetic plains, where 68.4 to 75.9 million metric tons of rice straw are burned annually in Indian cities, which already experience the worst air quality in the world. Air pollution drastically increases during the time of residue burning in the surrounding villages. Some studies indicate that the government regulation to save groundwater from the root cause of this unsustainable use of residues. In 2009, the state governments of Punjab and Haryana prohibited rice transplanting until the onset of monsoon in northwestern India to avoid overexploitation of groundwater, which not only delayed the rice harvest but also narrowed the turnaround time between rice and wheat, prompting farmers to burn the residue to quickly remove them from the field. In response to farmers burning rice residue, the government developed a national policy for management of crop residue to control residue burning and promote in situ crop residue management in 2014. This policy promoted the use of residues in power generation, production of bioethanol, composting, mushroom cultivation as packing material and input in the paper industry, charcoal gasification. It also encouraged the dissemination of conservation agriculture practices, incentivized the purchase of agricultural machinery that facilitates in situ crop residue management. In 2015, the National Green Tribunal banned crop residue burning in Rajasthan, Uttar Pradesh, Haryana, and Punjab. The Central Pollution Control Board and the penalty amount was based on the land holding size. Residue burning is also a punishable offense under the Air Act of 1981. Despite these regulations, farmers continue burning rice residue and pollution levels have not subsided in northwest India. Learning from the ineffective regulations, both the state and central government started to focus on technology-based solutions, including the promotion of agriculture mechanization for in situ crop residue management and the production of fuel and energy using excess crop residue. In the development and adoption of technological options to sustainably manage crop residue are dynamic, endogenous, and dependent on the relative scarcity of human labor versus land in the region. In some countries, the scenario of limited acceptance of technological innovations to sustainably assimilate crop residue in the soil was altered by information and service provision. Manage of crop residue. Managing crop residue involves the deliberate and strategic utilization of leftover plant materials from harvest to enhance soil health and productivity. This management of crop residue is a critical aspect of sustainable farming. The residue after harvest, if managed effectively, can provide numerous benefits. Farmers have a range of crop residue management choices, each with its own implications for soil health, crop yield, and environmental impact. The current crop residue management practices vary widely, reflecting the diversity of crops, climates, and soil. An approach to residue management involves taking into account these factors to make effective crop residue management decisions. Sustainable crop residue management is a complex task requiring knowledge, planning, and careful execution. Importance of managing crop residue. Crop residue management is important due to its numerous benefits. It helps in soil conservation by reducing soil erosion, preserving fertility. It also enhances soil organic matter, organic carbon, which are essential for maintaining soil health. This leads to higher crop yields. Effective management of crop residue also contributes to sustainable agriculture practices by reducing environmental pollution and promoting long-term agricultural productivity. Types of crop residue. Crop residue can be classified into various types, each with its unique characteristic and uses. These include stalk and stem residue, leaf residue, husk and hull residue, straw residues, root and tuber residue. Stalk and stem crop residues. Stalk and stem residue, primarily from plants like corn and wheat, are major agricultural crop leftover in monocropping system, particularly wheat cropping. Substantial residue production occurs, necessitating meticulous management to maintain soil health and fertility. Crop residue collection and harvest are critical practices in residue management. These residue can be used for agriculture and industrial purposes, but their use must be done responsibly to prevent exploitation and ensure ecosystem sustainability. Number two, leaf crop residue. Leaf residues derived from leafy vegetable and plants are a significant crop leftover in agriculture. They are essential components of plant biomass and play a huge role in crop residue mulching. Maintain ideal soil temperature. Leaf residue also enhance soil organic carbon content, providing nourishment to soil microorganisms and facilitating residue decomposition, improving soil fertility and crop productivity. Husk and hull crop residue. Husk and hull residues primarily from cereals and seeds post harvest are a significant portion of agriculture waste. Despite being undervalued, they provide a significant residue load. Proper management can make crop residue a valuable resource, reducing residue amounts and enhancing soil micronutrient availability. Straw crop residues. Crop residues consisting of stalk, stem, and leaves are a significant category of agricultural waste. They have various applications, including in the paper industry, where they replace wood. Straw choppers are used to manage straw distribution, promoting recycling of residue back into the soil. However, crop residue burning is less favored due to environmental concern. Root and tuber crop residue. Root and tuber crop residue, a type of agriculture waste, are most post-harvest leftover parts of plants like potatoes, yams, beets, and carrots. These residues are important for soil management, improving soil quality and fertility. The organic matter in these residues contribute to soil carbon, which boosts plant growth. Integrated crop management can efficiently utilize these residues to enhance the crop production and improve soil nutrient availability, thus promoting sustainable agriculture and bolstering soil health. Corn crop residue. Corn crop residue or corn stover are unused parts of the corn plants left in the field after harvest. They can be used for soil and moisture conservation as well as livestock feed. They also contribute to soil conservation and carbon sequestration, reducing greenhouse gases. Effective management of corn crop residues is important for sustainable agriculture, ensuring the health and productivity of the ecosystem. Techniques used for managing crop residue. There are several techniques used in the management of crop residue, each with its unique benefits and consideration. These methods include tillage, no-till farming, composting, mulching, baling. Tillage in crop residue management. Crop residue management involves using various tillage techniques to manage leftover plant material in the soil, preparing it for subsequent crops and improving soil tilth and water holding capacity. The choice of the technique depends on soil type, wheat cropping system requirements. Excessive tillage can cause soil compaction, affecting residue distribution and root growth. No tilling form allows soil to remain undisturbed, enhancing water holding capacity and reducing erosion. No-till farming in crop residue management. No-till farming is a technique used in crop residue management to preserve soil moisture and reduce erosion by leaving the soil undisturbed post-harvest. It is commonly used for row crops and ensures maximum residue retention, improving soil structures and moisture. This system also enhances soil productivity by increasing organic matter content, carbon sequestration, and promoting ideal tilling conditions. The inherent characteristic of leaving the soil undisturbed conserves its physical and biological properties, resulting in a sustainable and productive agricultural system. Composting and crop residue management. Composting is a method used in crop residue management, transforming residual biomass into valuable soil management. It involves controlled decomposition of plant remains, including grazing, crop, and final crop residue. This strategy reduces the need for burning residue, which can harm the environment. Composting improves soil quality, fertility, and structure, making it a sustainable alternative for farmers. Mulching and crop residue management. Mulching is an important method for managing crop residue, particularly cereal residue. This process involves spreading organic matter or crushed stones over the soil surface for protection and improvement. Mulching increases soil water holding capacity, reduces evaporation, minimizes erosion, and moderates soil temperature. It also mitigates negative effects of leaving soil bare, such as nutrient leaching and weed proliferation, making it a vital practice in crop residue management and contributing to sustainable agriculture. Baling in crop residue management. Baling is a technique used to manage crop residue, gathering and compressing residue like sugarcane bagasse into compact bales. This practice reduces input cost for farmers and enhances biogas. Enhances biogas yield when used for anaerobic digestion. Baled residues can also be used for burning in power plants, reducing greenhouse gas emission. Baling presents a sustainable approach to leveraging agriculture waste, offering both ecological and economic benefits. Conversion to bioenergy in crop residue management. Crop residue management is a growing global practice converting agriculture byproducts into bioenergy. This practice reduces fossil fuel demand and mitigates climate change under controlled traffic system, and no-till planters. Residues like wheat crop and rice straw are converted into biochar, a high carbon, fine grained residue that enhances component yield and soil fertility. Equipment used for the crop residue management. Various machinery such as disc harrow, vertical tillage tools play a crucial role in managing crop residue, preserving moisture content and controlling disease. The stripe till method, particularly vital for managing fungal disease in sugarcane, takes into account factors like soil type, crop type, and weather condition to optimize outcomes. The effectiveness of these techniques underscores the importance of selecting appropriate equipment, as the right tools can greatly enhance crop yield and disease resistance, leading a healthier leading to healthier, high-yielding crops. Incorporating these methods within organic farming practices further supports sustainable agriculture by reducing the need for chemical inputs and promoting environmental health. Benefits in managing crop residue. Managing crop residue effectively offers multifarious benefits across environmental, agronomic, and economic dimensions. Key advantages include soil health enhancement. Residue improves soil properties by adding organic matter, enhancing microbial activity for nutrient cycling and soil structure. Moisture conservation and erosion control. Residues cover the soil surface, helping retain moisture and protect against erosion, vital for soil conservation measures. Nutrient recycling and reduce fertilizer use. Decomposing residues recycle nutrient, reducing the need for synthetic fertilizer and enhancing the availability of micronutrients. Weed and disease control. Residue can suppress weed growth and help manage disease, reducing the reliance on chemical control methods. Sustainable farming. Incorporation into no-till and other conservation farming system reduces greenhouse gas emission and supports sustainable soil management. Economic efficiency. By improving soil fertility and structure, residues contribute to higher yields and reduce input costs such as fertilizers and pesticides. Additional uses. Beyond the field, crop residue have applications in reducing animal feed as raw material in the paper industry, potentially as gaseous fuel, offering economic and environmental benefits. Enhanced biodiversity. Residue management supports diverse biological activity in agriculture soils, promoting overall ecosystem health. Crop residue management impact on soil health. Crop residue management improves soil health and offer numerous agricultural benefits. It reduces water erosion by providing a protective layer, enriches soil with sulfur, and serves as a solid fuel source in thermal power plants. It also transforms agriculture waste into profitable oyster mushroom cultivation. Satellite imagery sources aid in residue management, ensure soil health. Crop residue management effect on erosion. Crop residue management is important for maintaining soil integrity and preventing water runoff. It acts as a protective layer, reducing water speed during rainfall and preventing soil displacement. This preserves soil nutrients and structure. The organic matter from crop residue also enhances soil water absorption, reducing erosion risk. Prudent residue management can significantly reduce erosion, safeguarding agricultural lands' long-term productivity. The challenges in crop residue management. Crop residue management has numerous benefits, but several challenges hinder its implementation. These include a lack of awareness among farmers, a shortage of necessary equipment and technology, especially in developing regions, additional labor and time requirements for small scale farmers, and potential policy and regulatory hurdles. To overcome these obstacles, all stakeholders must work together to ensure the successful implementation of crop residue management practices. The penalties for improper crop residue management. Improper handling of crop residue in agriculture can result in environmental degradation and reduced soil fertility, whereas appropriate management can boost soil health, lessen erosion, and increase crop productivity. Neglected residues might lead to pest infestation, disease outbreaks, nutrient imbalance, and air pollution. On the other hand, well-managed residues enhance soil organic matter, improve water retention, and promote a sustainable agriculture system. Integrated these residue management techniques into broader agricultural practices is important for maintaining the long-term viability and environmental sustainability of farming. Thank you. Please subscribe, comment, or like.